What do you think causes how fast that rotates? No, it's not actually. Voltage, this would get higher. When you talk speed, speed always incorporates something very important. It's the frequency that dictates how fast that goes. Frequency dictator. Very, very cool. Okay, so frequency tells me how fast that turns. Higher frequency, that's moving faster. Lower frequency, that's turning slower. When you get to VFDs, you'll see exactly what that's talking about. Now, all we have to do is explain this part. Now, a rotating magnetic field, we can all kind of agree that even though it's not truly rotating, it is rotating. In honesty, when you build this machine, these poles are half wound over top of each other. So as this field is collapsing, this field is rising. It's like a baton pass in a 4x100 meter relay. It's like everybody's doing the job and there's a smooth transition from one to the next. In reality, that's how it's wound. I have to draw it like this or it gets too ugly and full of too much stuff. Because all we have to do now is say, well, let's pretend that I'm going to take a rotor out of this thing, a squirrel cage induction motor. The stator does that job every single time. Rotating magnetic field, that's what it provides. That's what it does. That's its job. Let me put a rotor inside it. Rotor is the simplest design known to mankind. It's literally a bunch of laminated, silicone impregnated iron sheets with bars that go straight through it. So you see that dotted line? It's my hidden line. That's just showing that there is a rotor bar. Each one of those is a solid piece of aluminum, end for end. Solid piece of aluminum. That solid piece of aluminum, end per end, has a shorting ring, which is another thick aluminum ring that each of those bars attaches to on this end. And it's got a shorting ring on the other end, just like this. That shorting ring makes this point and this point and this point all the exact same energy. It's got 0 ohms. It is a big hunk of aluminum. And that's fun. And all we're going to do is we're going to put one rotor bar right in the middle of that. Now when I say in the middle, what we have to remember is this is a machine that's got a field that's moving. And I'm going to stick a rotor in there. So what I need to do is get rid of some of those lines. You guys understand the revolving part now, right? That part made sense? How it turns? Okay, go ahead. Yeah, snap photos any moment you want, you guys. Totally fine. Once you got that, you're like, okay, that's a rotating magnetic field. That's what we're talking about. Oh yeah, my students always take pictures, film, you name it. It's good to look back at later and just write some notes. Look at your photo and write some notes, because then you're like as soon as I'm done, write some notes on your pictures. You're good at what you got. That's cool. I'm going to get rid of all of the flux. We know it's there. We know it's rotating. Let's just keep that in mind. Okay. We don't even care about 1, 2, 3 anymore. What we care about is it's going clockwise. That was the actual goal there. Now what I'm going to do is I'm going to put a rotor in this thing. So here's my rotor. I definitely have to have a bearing. So motors have end bells on them. There's bearings in the end bells. That's to keep this rotor exactly centered in the middle of that magnetic field. It's got to be right in the middle, and nothing can touch. So here's my shaft through the rotor right here. It's got a bearing around it like this, and that's what allows it to spin freely with as little friction as possible. But the rotor bar, this guy right here, I'm just going to pick one. You got to remember there's a bunch of rotor bars. I'll pick one. And I'm going to put it right here. That's a rotor bar. This guy right there. So I placed the bar in there, and you've got to remember there's a whole bunch all the way around this. That's cool. There's a bar sitting in this thing, and this thing has a rotating magnetic field, which means if the rotor's not turning and it's sitting totally stationary and it's not moving at all, there's a bar, and there's a magnetic field that's going from here to here to here to here. Would you agree with that statement? Yeah. Okay, let's take a look at this statement here. Induction. There's a bar that's not moving, and I have a magnetic field turning. Is there relative motion between a magnetic field and something that can conduct? Would you say that there's relative motion? There has to be. Of course there is. This thing is actually spinning 3,600 RPM if that's a two-pole machine like I've drawn. That's how fast it's turning, 3,600 RPM. There is a lot of relative motion. between something that's not moving and a fan that's magnetic field, that's spinning 3,600, a ton of relative motion. Well, we already told each other, we already agreed on this. Induction, that principle is really cool. If there is relative motion between a conductor and a magnetic field, we will induce voltage on that conductor. So the moment that this field is turning and that's not moving, I induce voltage on that rotor bar, which means that rotor bar is sitting right there. It's 50 volts from one end to the other. It's actually got a potential across it. That's what induction actually is. If I want to make more volts on it, simple, huh? Increase the flux density, increase the length of that rotor bar, or increase the speed between the magnetic field and the rotor bar. From that, we could say, I got voltage. Now we have to remember, this thing with its shorting rings, yeah, there's voltage from here to here on that rotor bar. It's a dead short with these end rings to the next rotor bar, and the next rotor bar, and the next rotor bar, which means you put a whole bunch of voltage on something that's got like 0.0001 ohms. You've done Ohm's law, right? There's going to be current flow. When you agree, there's going to be current flow. I got 50 volts applied across something that is less than 1 ohm worth of resistance. Current flows through that rotor bar, rages through it. Remember I told you that, well, when we have a rotor bar, or when we have a conductor, and we put a current through it, it makes a magnetic field. It's at that moment a magnetic field is formed. And its direction rotates like that. There's a strong magnetic field around that rotor bar, a very strong one, because there's lots of current going through it. I got a magnetic field around this, and I got a magnetic field, a separate one that actually caused that one, but they're separate magnetic fields. I've got another one moving by it. Remember, they don't like to cross. So I have a magnetic field here, another one that's trying to go by it at 3,600 RPM. There is an instant force that's exerted. It's called Lorentz force. And it will take that bar and make it try to move that direction. Simply because this magnetic field is tearing lines of flux going by it, and you don't get something for nothing. You made a magnetic field, you pushed it past another one, there's going to be some work that happens there. The work turns into rotation. It causes that bar to want to move in exactly perpendicular directions to the magnetic field. 90 degrees to it, it wants to go that way. But luckily, we have it entrapped in a cylinder that's actually pivoting here. So even though the force that's exerted is 90 degrees to the magnetic field, it is like at right angles, that rotor bar can't go directly to the right, it starts to rotate on the arc. And all at the same time, that's happening on every single rotor bar in that field. All of them have that same effect taking place inside that machine, which now I amplify that small bit of force that's exerted on that one. I'll just magnify and amplify it by 20 times. Now I've got real force taking place. Well, now it rotates. And the whole time that magnetic field is moving past that conductor, there will exert a force. It will have a force exerted. It will cause it to rotate. And so as long as this is rotating, this is rotating. That's the induction motor principle right there. The cool part is we do it very simply by applying the right kind of voltage to the right kind of stator, and it's magic the way it goes. That is one of the most important inventions in the 1900s, that right there. That has done so much work for humankind in the last 150 years that it's unbelievable what this has done for us. How big do you think those get? Horsepower-wise? Massive. Biggest motor on Earth is about 5 years ago. NASA's wind tunnel. 50,000 horsepower. What's even cooler is it's on one variable frequency drive. So they can change the speed.
VFD?
One VFD, made by ABB, Azia Brown Bozer. One VFD, it's 5 stories high, the VFD. So they can change the speed of it for wind tunnel testing. 50,000 horsepower. Canfor and Taylor that shut down, the pulp mill, they had 727,000 horsepower motors there. They're that kind of motors. synchronous, we'll get to that in a minute. But still a motor. Younger plant, down there in Taylor, it's got a 13,000 horsepower fire pump. That's its fire pump. That place catches on fire, pulls straight out of the Peace River with 13,000 horsepower and pushes that water over top of all the vessels so they don't rupture. They fire it up once a year just to make sure it works. And when they do, they have to contact BC Hydro because it looks like a tree fell on the transmission line from inrush when they first turn it on. Big gauges at power producing plants go for current for a moment. What the hell was that? It's like, yeah, they have to notify Hydro. They're testing that motor in Taylor. And it runs at 13,800 volts. It runs at line voltage.
Don't they ramp it up on a VFD?
Now they do. They put a VFD in 3 years ago. A guy in my class was on the commissioning crew for it. It's like, yeah, it's very cool. That's so that they don't have to notify Hydro. They can slowly bring it up to speed to test it. No big current. Does that make sense, you guys, why a motor would turn? That's the key right there. Every motor turns off that same principle. Induced voltage on a rotor bar, the interaction between its magnetic field and the magnetic field that induced the voltage on it in the first place causes rotation. And that is really cool. So now, as we move through the terms, things become easier. You've heard the term slip, right? Slip is a weird thing. All squirrel cage induction motors suffer from slip, but I'm not going to call it suffer. They experience slip. It's a real thing. Slip means that the rotor inside here doesn't turn at the same speed as the magnetic field out here. Let me just put some words here. Slip. What slip is the RPM difference between the rotor and the magnetic field that's spinning. RPM difference. Between the rotor and stator. That's a statement. That's an easy statement. Let's just talk about why we have to have slip. I told you this machine was going 3,600 RPM. 3,600 RPM.
On a two-pole machine.
On a two-pole, yeah. You would calculate, you guys remember the formula for calculating the gun again?
Yep, we do, yeah.
You calculate what the slip, transpose that all you want, whatever you got. That's pairs of, or individual poles, not pairs of poles. You probably saw it with 60 and it's pairs of poles. They do all this stupid stuff. It's like, just pick one and use it. That one works every time. That's individual poles per phase. That's what that means. That math, 60 hertz, two-pole machine, you get 3,600 RPM. Slam dunk. That's actually called, this is important, that's called the synchronous speed of this motor. Synchronous speed. And in a squirrel cage induction motor, that's calculation. That's all it is, it's calculation. That's not what the rotor's turning. In this machine, it will never turn at the same speed as the calculated value, not possible. Let's just figure out why that's not possible. Let's pretend that I do all this magic we just talked about. This magnetic field is doing 3,600 RPM. And I'm going to pretend that the rotor is also doing 3,600 RPM. Coming back to induction, that's going 3,600 and that's going 3,600. Is there any relative motion between those two fields?
No.
No. If I have no relative motion between this magnetic field and that conductor, I have no flux on that conductor. If I have no flux on that conductor, I have no force exerted on that conductor. And so all of a sudden, slip is what keeps a motor turning. That's why it turns, because we always have an induced voltage on that rotor bar. If I don't have that, I don't have any force, I don't have any rotation. That's a squirrel cage induction motor that doesn't work. But the beauty is physics tells us, wouldn't matter, that's not possible anyway. Now it's gonna be possible with that other machine, but I have to have you know that other machine is special. It's got something different in it as well. It's not just like this. So we are gonna see that in a moment. But yeah, without that relative motion difference, I have no induced voltage. If I don't have induced voltage, I don't have a magnetic field. If I don't have the magnetic field, I got no force exerted on that rotor bar. That's why I have to have slip. What do you think makes slip get greater? This will never change. This 3600 right here, once that voltage is thrown on it at that frequency, that never changes. This stator, 3600. What could cause that rotor to go slower and slower and slower?
The frequency?
Yes, we could, but we're not. We're gonna leave the frequency the same. What else could cause a motor to slow down?
Load.
Load, 100% load. So you've probably seen this. Got a motor that's spinning. It's not loaded. We'll pick one. We'll pick an easy one. A table saw. Who's ever used a table saw? Please put your hands up. How about a skill saw? Yeah, any kind of saw. You know, you turn it on. And you start cutting wood. You know what's happening? Slip is increasing because we physically are holding that rotor from turning. Slip increases, so it's actually going slower than it was unloaded. If slip increases, this increases the relative motion difference between the rotor bar and the stator. If the speed increases, I will induce more voltage on the rotor bar. I will have more flux around that rotor bar. I will have more force exerted. The slower that motor goes, the more current goes through the rotor bar, the more force it exerts. Hence the table saw, spinning like mad, totally crazy. You slide a sheet of 1-inch teak into it. Holy man, if you're cutting that, you need a good table saw. Slide a big sheet into it, it's like, if you had an ammeter on those lines, oh yeah, the current just went up 4 times. You don't get something for nothing. You need more power to do this now. But inside that motor, it produces more force, more torque at a slower speed. It's the balance. It's teeter-totter.
You tell us the maximum 15% slip?
Yeah. After 15%, what typically happens is it just goes to stall speed. It just goes, and anybody that's run a table saw and run it too hard, who's experienced that? What's the next thing that happens? Click. That's why I have overcurrent devices. It's like, yeah, this thing's drawing 57 amps. That's called locked rotor current for a motor. All motors have locked rotor current. The most current that actually happens in a motor is the moment you energize the stator and that's not moving at all. As soon as it starts to move, all kinds of magic happens. We have this relative motion getting closer and closer and closer, so the speed difference is getting less and less and less. But what's really cool is this phenomenon that's all about magnetism. We produce something cool called counter EMF. Have you guys heard of that, counter EMF? Yeah, it's pretty awesome. That's a magnetic field right here in that rotor bar that's spinning. And as that rotor bar goes past all of the windings on these poles, well, it's a magnetic field that's actually inducing voltage on the poles as it goes by. Even though it's this double whammy. Counter EMF is literally what happens when I move that rotor bar with its own magnetic field past all the stationary coils. Holy shit! We use the stationary coils to make that field in the first place, then that field fights back. That's called counter EMF. That's what limits the current in a motor as it speeds up. Because as it speeds up, counter EMF, I can replace that E with CEMF. As it speeds up, my velocity increases. I would produce more counter EMF if I was focusing on the rotor. Like, wow, that is absolute magic. All machines have this cool phenomenon. In every motor, there is a generator effect. That's a generator effect. In every generator, there is a motor effect. And so suddenly it's like, man, those two things are the exact piece of equipment. Understanding one, you understand both of them. It's just applying it at the right time. That's it. You know one, you know both of them. DC machine, well, you can have a generator and a motor. They're the exact same machine. There's no difference between those two machines. This one you feed to the motor with electricity to make horsepower. The generator, you feed horsepower to make electricity. But it's the same machine, physically. Same windings, same rotor, same everything. Well, that's actually really cool. The theory is the important part. Understanding what goes on with all this is the important part. Funky, eh? I'll pause. Any questions on that squirrel cage for now? We don't want to do too much. Like, I can't talk about this for 3 hours straight. I mean, I spend 5 days in third year going through every part of this now. This is the intro every time. It's like, you got to know this part. From here, we talk about all that other stuff. You won't need to know that. Principle of operation. That's what you need to know. Not bad? making enough sense so far. Honestly, once that starts to make sense, the induction thing, and everything hinges off of that in the electrical world. Induction is the thing, that all of it. We run wire to make magnetic fields, because magnetic fields, that's induction, that does magic, that does cool things. Now it's an easy step. We're gonna go into the synchronous motor. We're actually just gonna have this as the next part. Let's take a 5-minute get up and stretch break, go to the bathroom, bio break. You can pause the video just so that it's like you're not standing there the whole time.